Am I audible? Hi, am I audible? Good evening, everyone. Welcome to Goscore Learning, the fastest growing edtech industry in Middle East. I'm your Dhanya ma'am with the revision of Chemical Kinetic chapter, that is grade 12 chemistry. Okay, so today we are going to revise the Chemical Kinetics chapter. I'm giving you the major important topics that we covered under this Chemical Kinetics chapter. Are you all ready? Can we start? So, we all know that chemical kinetics is the branch of chemistry that deals with the rate of a reaction, that is the speed of a reaction. The branch of chemistry which deals with the study of reaction rates and the mechanism is what we call the chemical kinetics. So, if you consider the reaction, reactant are changing into product. We know that during the reaction, what actually happens, the reactant molecule is converting into product. So at the start of the reaction, there will be more amount of reactant and the product concentration will be, or the amount of product will be very less, right? As the reaction proceeds, what happens? The amount of the reactant starts decreasing and this reactant molecules get converted into products, right? So what we can say, as the reaction proceeds, the amount or the concentration of reactant is decreasing and the concentration or the amount of product is increasing, right? So if you consider the reaction are changing into product, we can say the rate of reaction as change in the concentration of reactant or product with the specified time, right? So we can write the rate is equal to change in the concentration of either reactant or product. That means whether the reactant is decreasing or the product concentration is increasing with the time taken. Okay. So the rate is equal to the change in the concentration of reactant or product divided by time taken. Okay. Now, as I told you, we can express the rate of reaction in terms of reactant as well as in terms of product, right? In terms of reactant, what we can say, rate of reaction is the decrease in the concentration of reactant. In terms of product, it is increase in the concentration of product. So, here we can express the rate of a reaction in terms of reactant as well as in terms of product, right? In terms of reactant, it is rate of disappearance or decrease in the concentration of reactant. So, in that case, the rate of reaction is equal to, just a moment, yeah, rate of reaction is the decrease in the concentration of reactant. It's clear that as the reaction proceeds, the amount or the concentration of reactant is decreasing because the reactant is converting into product, right? So, in terms of reactant, what we can write? Rate of reaction is the decrease in concentration of reactant divided by time taken. And in terms of product, what we can say? Rate is the rate of appearance of product or rate of increase in the concentration of product, right? So in that case, the rate of reaction is the increase in the concentration of product divided by time taken. Okay. So these are the two methods, two ways we can express the rate of reaction. So if you consider the reaction A plus B giving product C, how we can write the rate of this particular reaction? Rate is equal to decrease in the concentration of A. Okay, so there will be a change in the concentration, right? If you consider for a particular time interval, definitely there will be a change in the concentration of reactant as well as in the product, right? So that change we will be denoting by D. That is small change in the small fraction. That dA Why I am putting the square bracket? If you write the thing in the square bracket, it indicates concentration. So this A within the square bracket indicate the concentration of that particular reactant A. Okay, if you are writing B, that is the concentration of B. Okay, so dA by dt. Since it is a reactant, what happens during the reaction? There is a decrease in the concentration. So as A is a reactant, I have to put my negative sign here. So in terms of reactant A, how we can say the rate is equal to minus d concentration of A with change in time dt. Or in terms of B, reactant B, how can I write the rate? It's equal to minus d concentration of B divided by dt. Why I put the negative sign? Because B is also a reactant. As the reaction proceeds, what happens? There will be a decrease in the concentration of B. That's why I put the negative sign there. Okay. In terms of product C, how we can write? D into D concentration of C. Change in the concentration of product C by time. Okay. So this is what how we can express the rate of reaction in terms of reactant and in terms of product. Okay. Now let's see what you mean by the, okay, before that, let's see what is the unit of rate of a reaction. So rate, how we are expressing the rate? Rate is equal to, rate is nothing but the concentration. Okay, if you are expressing in terms of concentration of reactant or product, the numerator will always be the concentration, right? The denominator will be time. So, what will be the unit for concentration? It will be mole per liter divided by time will be in second. So, what will be the unit of rate of a reaction? Rate is equal to mole liter inverse second inverse. This is what the unit of rate of a reaction. The unit of rate of reaction is mole liter inverse second inverse, right? Okay. Now let's see. We can express the rate in terms of two ways. That is the instantaneous rate and average rate. Now, what do you mean by this average rate? Average rate is nothing but we are finding out the rate of reaction over a particular time interval. Okay. The change in concentration over a time period is represented by the average rate. Okay. So there we are considering a time frame. So there will be a more changes in the concentration as well as in the time. Okay. So how we will represent if you consider the same reaction A plus B giving the product C, how we will write the average rate? Average rate we are representing with our average. How we can write there? We can't use the term D because it's for small fraction changes. Here large changes in the concentration is there. So we will put the delta. Okay, delta concentration of A divided by delta T. Since A is the reactant, we have to put a negative sign. Okay. Or in terms of B, we can write delta concentration of B by delta T. Or in terms of the product, we can write delta concentration of C by delta T. That is the way of representing average rate of a reaction. Now see the instantaneous rate. From the word itself, it's clear. Instantaneous rate means the rate of a reaction at a particular instant. Okay. The rate of change in concentration at a particular time is what we call instantaneous rate. So, instantaneous rate, the changes will be very small. So, we will be representing with D. So, we can write the same reaction. We can write the same reaction instantaneous rate is equal to, for the same reaction, it will be minus D concentration of A divided by dt. Or why I am taking D? Because There only a small changes will be there because we are considering for a very small fraction of time, right? So it will be minus dA by dt, dB by dt, what is equal to d concentration of product with that small changes, that particular time. Okay. So this is the average rate and instantaneous rate of a reaction. And one more thing is there, here all in this equation for all the reactant and product, the stoichiometric coefficient is 1, right? If the stoichiometric coefficient is different, just take the example AA plus BB giving CC product, in which the small letters represents the stoichiometric coefficient of the balanced chemical equation, and the capital letter A and B represents the reactant and the C represent the product. In this case, how we will write the rate? Rate is equal to, we have to take the reciprocal of the stoichiometric coefficient, that is in terms of reactant, stoichiometric coefficient is A. So we have to take the reciprocal, 1 by A d concentration of A divided by dt. Since it is a reactant, we have to put a negative sign there. Okay. Or is equal to negative 1 by B d concentration of B by dt. Same way you can write for product also, that's equal to 1 by C d concentration of C by dt. Okay. That's about the rate of a reaction. Now let's see what will be the, for this, just see. Okay. Now let's see what will be the unit for this rate of, okay, we have already discussed the unit of rate of a reaction, right? Okay. Now we can discuss the factors affecting the rate of a chemical reaction. Okay. Before that, I would like to give you the graphical representation. Okay. So here, if you are taking the concentration in the y-axis and time in the x-axis, that we are plotting a concentration versus time graph. In that, we know that as the reaction proceeds, initially the concentration of reactant will be higher, and as the reaction proceeds, what will happen? The reactant concentration starts decreasing. So this will be the, as the time passes, the concentration of reactant decreases. So this graph represent the reactants, right? Then what about the product? Initially, the product concentration will be 0, right? As the reaction proceeds, the concentration of product increases. So this will be the graph for products, right? Clear? Okay. Now let's see what are the factors affecting the rate of a chemical reaction. Okay. We know that there are a number of factors which affect the rate of chemical reaction. The first one is the concentration of reactant. It's a clear fact that as you increase the concentration of reactant, the rate of the reaction will be faster. Okay. So we can say that rate is directly proportional to concentration of reactant. Next one is the temperature. As the temperature increases, the particle will move faster and there will be increase in the rate of a reaction. The next one is the presence of catalyst, that we already know that the catalyst will increase the rate of a reaction. We will be discussing these three factors in detail in the following slides, and there are other factors like nature of the reactant, surface area of the reactant, as well as the presence of light. We know about the photochemical reactions, right? There are certain reaction which will be fastened in the presence of sunlight. That is what we call photochemical reactions, right? So these three are the main factors that we want to discuss in this particular chapter. Okay. Now let's see very important in this chapter, that is the rate low. Okay. So as the factors, in the factors affecting the rate of reaction, we have told that the rate is always directly proportional to concentration of reactant, right? Now consider the reaction A plus, okay. Consider the reaction AA, where small a is the stoichiometric coefficient giving. Okay. For this particular reaction, what we can say, the rate is directly proportional to concentration of reactant. Here the reactant are A and B, right? So for writing the concentration, we will be putting it in a square bracket. Okay. So what we can say, rate will be directly proportional to concentration of reactant. Okay, A and B. So when you change this proportionality, what we can write, rate is equal to K, where K is the proportionality constant and is called as rate constant. Rate constant K into concentration of A into concentration of B. And a very important thing that you have to keep in mind is that the rate of reaction is always a experimental value. We cannot merely predict the rate of a reaction by simply looking at the balanced chemical equation or the theoretical basis. The rate of reaction is always calculated based on the experimental data. So here each concentration terms may be raised to a power that x and y. In certain reaction, this x and y value may be equal to the stoichiometric coefficient, but in certain reaction, it may not be equal to the stoichiometric coefficient. So it's not mandatory that this x and y value should be equal to the stoichiometric coefficient in the balanced equation. Okay. So here what we can write, rate is equal to rate constant K into concentration of A raised to power X. This X may or may not be the stoichiometric coefficient of reactant A into concentration of B raised to exponent Y. This Y may or may not be. It can be equal to B, it cannot be equal to B. It depends upon the what the value we are getting after the experimental data. Okay. So this is what the rate law. Now see, rate law. Rate law is the expression in which rate of a reaction. Okay. The rate of a reaction is given in terms of what? Molar concentration of reactant with each term raised to a power. Okay. Rate of reaction is expressed in molar concentration of reactant with each term raised to a power which may or may not be equal to the stoichiometric coefficient in the balanced chemical equation. That is what the rate law. If you know this expression, you can write explanation for the rate law. The rate law is the expression in which the reaction rate is given in terms of molar concentration of reactant with each term raised to some power which may or may not be equal to the stoichiometric coefficient of the reacting species in a balanced chemical equation. That means this x value may be equal to A or may not be equal to A. This y value may be equal to the small b or may not be equal to this b. Okay, that is what the rate law states. Okay, I hope it is clear. Now, see the order of reaction. As we have wrote, the rate as per the rate law, rate is equal to rate constant K. Just a moment, I'll write it here. As per the rate law, rate is equal to rate constant K into concentration of A raised to X into concentration of B raised to power Y. Okay, so you have two terms here as the exponent. The sum of this exponent in the rate law expression of the reaction is what we called, this is represented by N, this is what we called order of that particular reaction. Order is nothing but the sum of powers of the concentration of reactant. we are expressing the rate of reaction as per the rate law like this. In that, what is the exponents of the concentration terms? The sum of that exponent is what we call the order of that chemical reaction. So order can be values 0, 1, integer values, whatever it is, fractional values. Order can have any values, right? See, if this x and y value is 0, okay? If this x value 0, y value 0, that means x plus y will be 0. Then it will be a 0 order reaction. If this x is 0 and y is 1, then reaction will be first order reaction. If this x is 1 and y is 1, the reaction will be second order reaction. Like that, if you get the exponents in the rate law expression, we can say whether the reaction is following 0 order, first order, second order, third order, etc. Okay. So, the order of reaction is clear, right? Now, let's see what will be the unit for rate constant. Here, this K is what the rate constant. See? So, we can find out what will be the unit for rate constant. Rate constant K. Right? See. Here, what we can write? Rate constant K is equal to rate divided by concentration of A raised to X into concentration of B raised to Y. So, I am taking this K here, taking this concentration terms on left hand side. So, what will be the unit of rate? It is mole, liter inverse, second inverse, right? What will be the unit for concentration of A? It will be concentration is mole per liter raised to X. Concentration of B is mole per liter raised to exponent Y. Right? Since these two are same, how can I write rate constant K is equal to what? Mole, liter inverse, second inverse divided by mole per liter x plus y, right? What is x plus y? It is the order n, right? So, it will be mole liter inverse second inverse divided by mole per liter whole raised to n. That we can rearrange as K is equal to mole raised to 1 minus that we can write as mole raised to 1 minus n liter raised to n minus 1 second inverse. This is the very important one. You have to know that if you get any order, if n is 0, the reaction is a 0 order, you can find out the unit of rate constant by simply substituting 0 value here. Okay. So, what you will get? Mole raised to 1 minus 0. It is mole raised to 1. Liter raised to 0 minus 1. Liter inverse. Second inverse. If it is a first order reaction, what will be the unit for rate constant? It will be mole raised to 1 minus 1, that is 0. Any power raised to 0 means it's 1. Liter raised to 1 minus 1, liter raised to 0. Then K will be second inverse. Like that, if you know this, you can easily find out the unit of rate constant for any order reactions. Okay, you have to learn this very well. Okay, that's about the order of reaction. Now, let's see the next term. We have discussed all this order, the numericals, everything related to that in our each and every part about this chemical kinetics chapter, right? Now, let's see what you mean by the molecularity of reaction. Molecularity is nothing but the number of molecules or number of ions or species that actively participated in the chemical reaction. The number of reacting species that taking part in an elementary reaction. What do you mean by this elementary reaction? Elementary reaction means the reaction which takes place in a single steps. Okay. In an elementary reaction which must collide simultaneously in order to bring about the chemical reaction is called molecularity of a reaction. Simply means when a reactant is changing into product, how many molecules or how many ions of how many reacting species of reactants are involved in that particular reaction for getting converted into product. That number of reacting species is what we call molecularity. If in a particular reaction only one molecule of reacting species is there, then it is called a unimolecular reaction. If in a particular reaction, if there are two molecules of reacting species, then it is called bimolecular reactions. If there are three reacting species, then it is called trimolecular reactions, right? Okay. Now let's see the comparison between the order and molecularity. This is also a very important question in this chapter. That is, we know that order, it is the sum of the exponents in the rate law expression of a chemical reaction or sum of the powers of concentration of reactant in the rate law. Whereas the molecularity, it is the number of reacting species or reacting molecules that must be actively involved in the particular reaction. This order value, as I told you, it can have value, zero value, it can be fractional values, it can be integer values, because how we are expressing the rate? Rate is equal to k into a raised to power x and b raised to power y. This x and y values we are finding out by experimental data. So this can be have values as the fractional value 0 or integer values. But when you come in terms of molecularity, can molecularity be 0? There is 0 reacting molecules. Will the reaction proceed? No, right? So the molecularity will always be a value, integer value greater than 0. Okay? And this order we can apply for elementary as well as complex reaction, but the molecularity will be applicable only for elementary reaction. Okay, we know that the order, it's an experimental quantity, whereas the molecularity, it's a theoretical quantity. These are the four major differences between the order and molecularity of a reaction. Okay. Now, let's see what you mean by pseudo-first order reaction. What is actually the word pseudo? Pseudo means false. Okay? False first order reaction. So, that means the reaction is actually not following the first order, but due to certain conditions, the reaction will follow the first order kinetics. That type of reactions are called pseudo first order reaction. The reaction which is not truly of first order, but under certain conditions become reactions of first order is called a pseudo first order reaction. See, here I have two reacting species A plus B giving C. When you see the reaction itself, you will say it's a second order reaction, right? So how we will write the rate will be equal to K into concentration of A raised to X and concentration of B raised to Y. Since the molecular numerical, if you find out, we will get the value 1 and 1. You will be think it will be second order reaction. But if the concentration of B is higher, if there is more concentration of one of the reactant, what actually happened when you consider the change in the concentration, the one of the reactants change will be very negligible compared to the next one. So here the rate will be depending only on the concentration of reactant which is present in lesser quantity. So rate will be equal to K into concentration of A. So see, now the reaction follows first order kinetics, right? Actually, the reaction is not of first order kinetics, but due to certain conditions, the reaction follows the first order kinetics. That type of reactions are what we call pseudo first order reactions, right? Now, Let's take the examples. You should be very familiar with these two examples which is provided in the NCERT reader. The examples is for pseudo first order reaction. The first one is the hydrolysis of ester. So if you are getting a question that write the order for pseudo hydrolysis of ester, it should be coming to your mind that it is a pseudo first order reaction. So if they are asking for you to write the unit of rate constant, you have to substitute the n value 1 in that particular case. Okay. Now see the hydrolysis of ester, it will be, we are taking the ethyl acetate, that is CH3COO C2H5 plus H2O. Since here the water concentration is more, what actually happens? See, it will be breaking down to give CH3COOH plus C2H5OH, right? Here the rate of reaction is equal to water amount or water concentration will be very higher, and we will consider the concentration of A only for the rate expression. So rate is equal to K into concentration of ethyl acetate. Okay, now see, this is an example for pseudo first order reaction. Same like that, another example is the inversion of cane sugar. Cane sugar is C12H22O11. That inversion, it will give glucose plus fructose. In this case also, the rate of reaction depends only on the concentration of cane sugar. So that means it also follows pseudo first order reaction. Okay, that are the two very important examples for pseudo first order reaction, that is the hydrolysis of ester and inversion of cane sugar. So when you get a question like this from hydrolysis of ester and inversion of cane sugar, you should be familiar that it is a pseudo first order reaction. Okay. Oh. Now see the important term in this chapter, that is the integrated rate equation. We know that integrated rate equation will be different for different orders. So first we can see zero order reaction. So what do you mean by zero order reaction? That the sum of the exponent will be 0, right? So when you are expressing the concentration, how will be? Rate is equal to K into concentration of A raised to X and concentration of B raised to Y. So for zero order reaction, that X and Y terms are 0, right? Then it will be A raised to 0, B raised to 0. Any number raised to power 0 means it is 1, right? So rate is equal to K. Isn't it? So what we can say? Zero order reactions are those reactions in which the rate of reaction is proportional to the zero power of the concentration of reactant. Rate of reaction is proportional to the zero power of the concentration of reactant. Or zero order reactions are those reactions in which the rate of reaction is independent of the, not at all depending on the concentration. What we get here, rate is equal to rate constant K. So what we can say, zero order reactions are those reactions in which the rate of reaction is independent of the concentration of reactant. Okay. Now let's see the integrated rate equation for a zero order reaction. Okay. Consider the reactant changing into product, right? So, as per the rate law, since it is a zero order reaction, what will be the rate? Rate is equal to rate constant K, right? Since it is a zero order reaction, it will be A raised to power 0 and B raised to power 0. So, the rate is equal to K into 1 into 1. That will be equal to K. So, what is the rate? Decrease in the concentration of reactant. Here, reactant is R. So, decrease in the concentration with the time dt is equal to K. Right? So, I can write it like dr is equal to k into dt, and I am taking this negative side here. Negative side to this right side. So, dr is equal to minus k dt. When time t is equal to 0, what will be the concentration of r? It will be 0, right? When time t is equal to t, what will be the concentration of r? R will be t, isn't it? When 0 time, R0, initial concentration of reactant. As the time passes, the concentration changes to RT, isn't it? Now I am integrating this equation with upper limit, the initial concentration, sorry, lower limit, the initial concentration, and upper limit, the concentration at a t time. What I will get? dr is equal to minus k into time is 0 to t. Lower limit is 0, upper limit is t dt. So, it will be upper limit r t minus r0 is equal to minus k into t, right? So, I am taking the negative sign to this side. How can I write? R0 minus concentration of reactant at t time is equal to Kt. Or I can write the rate constant. K is equal to R0 minus RT by T. This is what the rate integrated rate equation for zero order reaction. Okay. So, this is for the zero order reaction. Now, let's see the graph that we can plot. Just keep in mind this equation. See, as per this equation, what we wrote, RT minus R0 is equal to minus KT, right? That is, okay, I'm rewriting this equation as RT is equal to minus KT plus R0. This will be same as Y is equal to mx plus c. That is the equation for a straight line. So, if I am plotting the y, rt versus time, see, rt on the y-axis, t on the x-axis. Since it is for a straight line, I will be getting a graph like this with the slope. What is the slope here? It is minus k. And what is the y-intercept? If you extrapolate the graph to y-axis, the y-intercept will be r0. So, this is what the graphical representation of zero order reaction. Okay. Now see the examples is for zero order reaction. That is the enzyme catalyst reactions is an reaction which occur on the metal surfaces are of zero order, and the decomposition of gaseous ammonia in presence of platinum and at high pressure will always follow the zero order kinetics, and the thermal decomposition of hydrogen iodide on gold surface is also a zero order reaction. So, you should be familiar with this examples which is provided in the NCERT reader. So, these three reactions follow zero order kinetics. Okay. Now see the integrated rate equation for first order reaction. Okay. So for first order reaction, consider the reaction reactant giving to product. How we can express the rate law? Rate is equal to rate constant K into concentration of reactant raised to power 1, since it's a first order reaction, right? Rate is decrease in the concentration of reactant with time minus dr by dt. That is what the rate, right? So, it's equal to what we got, K into R. Okay. So, I'm just rearranging this equation as minus dr by concentration of R is equal to K into dt. I'm taking this r to the side, dt to right side. Okay. This one I can rewrite as d into concentration of r by concentration of r is equal to minus k dt. Same like as we taken for the zero order reaction. When T is equal to 0, R will be equal to R0. When T is equal to T, what will be the R value? Will be concentration of R is represented by RT. Then you have to integrate it, right? With upper limit on the left side, sorry, lower limit R0 and upper limit RT D concentration of R by concentration of R is equal to minus K into 0 to T dt, right? So, what is dr by R? It is natural log R. ln R with upper limit, lower limit R0 and upper limit R is equal to minus K, right? K0 T, KT. Okay. So, when you put the upper and lower limit, what you will get? ln RT minus ln R0 equal to minus KT. Okay. So, when you change the natural log to log, how we can convert ln to, how we can convert natural log ln A to log A? It will be 2.303 into log A, right? Same way we can convert this into natural log, then it will be log RT minus log R0 is equal to minus KT for log 2.303. Okay, 2.303 whole into log RT minus log R0 is equal to minus KT. So, it will be log RT minus log R0 equal to minus KT by 2.303. I am taking the negative sign to this side. It will be log R0 minus log RT is equal to KT by 2.303. Right? So, this one I can write as, we know that log A minus log B is equal to what? Log A by B, right? Same way I can rewrite it as log R0 by RT is equal to KT divided by 2.303, or you can rewrite it as K is equal to 2.303 by T into log R0 by RT. Okay, that will be the rate constant for, or integrated rate equation for first order reaction. That you can write. You can keep K here. You're taking 2.303 this side, 2.303 divided by T into log R0 by RT is equal to K. That is what the rate expression for first order reaction. Now let's see here. We have got the log R0 by RT is equal to K into K divided by 2.303. This is what the graph equation we got, right? Log R0 by RT is equal to KT divided by 2.303. What I told you, you can write K is equal to 2.303 divided by T log R0 by RT. This is what the rate expression for a integrated rate equation for a first order reaction. Now see this one, I can rewrite like this. Is it all? See, right, I'm putting a plus 0 there. So now see, this is the y equal to, this all term will be m, t is x plus c. Since y-intercept is c, your graph will be, if you are plotting a graph of log r0 by rt versus time, since the intercept is c0, your graph will be originating from the origin and you will be getting a straight line like this with the slope. M value is k by 2.303. This is what the graphical representation for a first order reaction. And also we got the equation like this, right? ln RT. See here what we got. I have put in the box ln RT minus ln R0 equal to minus KT, right? So if you are rewriting that equation ln RT minus ln R0 equal to minus KT, you can rewrite it as natural log of RT is equal to minus KT plus ln R0. This will also be in the form of y equal to mx plus c. You are plotting the ln RT on the y-axis, time on the x-axis. You will be getting a straight line with the y-intercept ln R0 and slope minus k. See, this is the graph you are getting with the slope minus k, and you extrapolate the graph to y-axis. The y-intercept will be ln R0. Okay, so you should be familiar with this two graphical representation for first order reaction. Okay, now see some examples is for first order reactions. That is the hydrogenation of ethene is an example of first order reaction. Natural and artificial decay of unstable nuclei take place by first order kinetics, and the decomposition of N2O5 dinitrogen pentoxide and N2O are first order reactions. Now see the term half-life of a reaction. What do you mean by half-life? Half-life is nothing but the time taken to reduce the concentration of reactant to half of its initial value. Okay, the half-life of a reaction is the time in which the concentration of reactant is reduced to 1/2 of its initial concentration. So if you are taking the initial concentration as R0, the time taken to reduce the concentration to R0 by 2, that is what we called the half-life, which is represented with T half. That is what? Half-life of a reaction. Now see for the half-life for first order reaction, what do you get for the integrated equation for a first zero order reaction? That is R0 minus, sorry, what do you get for the equation for zero order reaction? R0 minus RT divided by is equal to K. This is what our integrated rate equation for zero order reaction, right? So, when the time T is equal to T half, half-life means the concentration RT is equal to, what is the half-life? The time taken to reduce the initial concentration to half-life. So, at that time, the reactant concentration will be half of the initial value, right? R0 by 2. So, if you substitute these values in this equation, what you will get? R0 minus, instead of RT, what we can write? R0 by 2 whole divided by T is half-life, right? Now, T is T half is equal to K. So, I'm taking the T half this side. T half is equal to 2R0 minus R0, that is R0 divided by 2K, right? This is what the half-life of a zero order reaction. Now see, the half-life of zero order reaction is directly proportional to the initial concentration of reactant. Okay, that means the half-life of zero order reaction depends on the initial concentration of reactant. So This expression is very important. You will be getting numericals based on this one. Find out the half-life of a zero order reaction. So T half is equal to, for zero order reaction, T half is equal to initial concentration divided by 2 into reaction rate constant. Okay. Now let's see the half-life for first order reaction also. For the first order reaction, what the equation that we learned, it is equal to K is equal to 2.303 by T log R0 by RT, right? So for first order reaction, same like what we did for the zero order, when T is equal to T half, what will be the RT value? It will be equal to half of the initial concentration. Just substitute those values in this equation. What you will get? K is equal to 2.303 divided by T is T half. Now log R0 by RT value is R0 by 2, right? These two terms get cancelled. This 1 by 2 will be log 2, right? Then what you will get? 2.303 by T half into log 2. Okay, now I am just rewriting this. T half is equal to 2.303 into log 2 divided by K. This, when you multiply log 2 value with 2.303, you will get 0.693 divided by K. This is what the half-life of first order reaction. See, for the first order reaction, the half-life is not at all depending on the initial concentration of reactant. But for zero order reaction, the half-life is directly proportional to the initial concentration of reactant. Right? That's about the integrated rate equation. Now let's see the temperature dependence of the rate of reaction. That is, when the temperature T is equal to T, the rate constant is K. When you increase the temperature by 10 degrees Celsius, you can see that the rate constant has become double the value. With a rise in the by 10 degrees Celsius, the rate constant is nearly doubled, and the effect of temperature on the reaction rate is given by the Arrhenius equation. That is, according to Arrhenius equation, K is equal to A into e raised to minus EA by RT, where K is the rate constant, A is the Arrhenius factor, EA is the activation energy, and R is the gas constant, T is the temperature in Kelvin. Okay. Now see, I'm taking the natural log on both sides. You can write ln K is equal to ln A into e raised to sorry ln K is equal to ln A into e raised to minus EA by RT. That I can write as ln A plus ln e raised to minus EA by RT. Right? That is natural log K is equal to natural log of Arrhenius factor A minus EA by RT natural log E. ln E value is 1. So, what we can write? ln K is equal to ln A minus EA by RT. If I am converting the natural log to log value, it will be 2.303 log K is equal to 2.303 log A minus EA by RT. Right? So, what you will get? Log K is equal to log A minus EA by 2.303 RT. This is what the Arrhenius equation. Log K is equal to log A minus EA by 2.303 RT. Okay. So, if you have this equation, you should be very familiar because you will be getting the numericals based on this. So, what do we get here? Log K is equal to log A minus EA by 2.303 RT. Okay, so if I have two rate constants K1 and K2 at temperature T1 and T2, what will be the new equation? That is also very important, very important equation, that is log K2 by K1 is equal to EA by 2.303 R into 1 by T1 minus 1 by T2. This is a very important equation. We have discussed this equation and its derivation in detail in the part 2 video of chemical kinetics. You can refer it, and this is also a very important. You will be getting numericals from this particular equation. Okay. It's very important. Arrhenius equation for two rate constant K1 and K2 at temperature T1 and T2. Okay. Now, what is actually mean by this activation energy? We have discussed the term EA here, right? Activation energy, EA. What is it? See, here hydrogen, I can represent it like this, right? And iodine, I2, it will be like this, right? So what actually happens is when these two react, this hydrogen, this iodine, they will form a new bond in between them. Okay, this is an intermediate complex and it is very unstable one. Okay, unstable complex. So, as since it is unstable, it will be breaking down like this to form what? Two hydrogen iodide. Okay, now see, the energy required to form the intermediate. The energy that is required to form this intermediate is what we called the activation energy. The energy required to form the intermediate called the activated complex, which is unstable, is known as the activation energy and is represented with E subscript A. Okay, when you plot the potential energy versus reaction coordinate, initially the reactant level was like this, then it will form an activation complex, then the product is forming there. Okay, now increase in the temperature of the substance. As we told, when you increase the temperature, the rate of reaction is increasing. As you increase the temperature, the substance increases as you increase the temperature of the substance, it will lead to increase in the fraction of molecules which collide with energies greater than A. See, when the temperature was T, only this much fraction of molecules possess the activation energy. When you increase the temperature, you can see the graph get widens and more number of molecules get activation energy and the reaction rate will be fast. Okay. Now see, what is the catalyst? We know that the catalyst is a substance which increases the rate of reaction without itself being undergoing any permanent change. So after the chemical reaction, the catalyst will increase the rate of reaction, but itself it won't undergo any chemical change. Okay, it just help to increase the speed of the reaction. So catalyst act by forming an intermediate complex. See, if we have two reactant A plus B and if X is the catalyst there, actually what happens is this catalyst will form a intermediate complex with this reactant. See, A catalyst B. Okay, since this is an intermediate is unstable, it will be breaking down to form the product and the catalyst get free. Okay, so the catalyst, it won't undergo any chemical change during the chemical reaction. It just helps to increase the rate of the chemical reaction. Okay. Now see, the catalyst provides an alternate pathway by reducing the activation energy between the reactant and product. That's why it will lower the, see, if you are plotting the concentration product coordinate, without catalyst, you will be getting a graph like this. In the presence of this much of activation energy as needed. In the presence of catalyst, you can see that the molecules, the activation energy getting lowered, more molecules will possess the activation energy and the reaction will proceed in a faster way. Okay, now see the characteristics. This is very important. The characteristics of catalyst, that is, a small amount of catalyst can catalyze a large amount of reactants. And the very important point is that catalyst does not alter the Gibbs energy, that is the delta G of a reaction. Catalyst will not alter the Gibbs energy, that is the delta G of the reaction. And the catalyst catalyzes the spontaneous reaction. It does not change the equilibrium constant of the reaction. Catalyst will catalyst both forward as well as backward reaction. It catalyzes both the forward as well as backward reactions. These are the main characteristics of catalyst. Now let's see the collision theory of chemical reaction. As per the collision theory, we are considering the reacting molecule, reacting species as spheres. Okay. So, according to collision theory, a chemical reaction is proceeding when this reacting species collide with each other. Okay. That all the collision won't give the product. Only the collisions with the proper orientation will provide the product. Okay. The reactant molecules are assumed to be hard spheres and the reaction occurs when the molecule collide with each other. So, if you consider for a unit volume, the number of collisions per second is what we call the collision frequency, represented with the letter Z. The number of collisions per second unit volume of the reaction mixture is called the collision frequency. Okay, and I told you not all the collisions will give the product, right? So, the collisions which were effective is what we called effective collision, and the collisions in which the molecule collide with sufficient kinetic energy and in proper orientation. The reacting molecules should be colliding with the sufficient energy to make the product, as well as it should be colliding in a proper orientation, then only the reaction will proceed. So, as to facilitate the breaking of bond between the reacting molecules and leading to the formation of new bond to form product. That is what we call the effective collision. Only the effective collision will lead to the formation of product. Not all the collisions will lead to the formation of product. Only the effective collision, that is the collisions with the sufficient kinetic energy and proper orientation will only provide the product or will only lead to the formation of new bond to form product. That's about the effective collision. These are the main topics that we have covered in this particular chapter, and there are a lot of numericals based on the equations that we learned in this chapter. So, I have done all the numericals in our 3-part videos of chemical kinetics chapter. You can go through that for referring the numericals. So, with this, I am winding up the revision of chemical kinetics chapter. I hope it is useful for you all. And on 19th December, Tuesday, your Nandini ma'am will be coming with the 6th chapter, that is the electromagnetic induction, second part. So, stay tuned with us. Thank you all.